Hello world, this is Craig. I thought we'd do a primer on the 80-80-85 stack. So the first question is, what is the stack? Well, the stack is simply a collection of either registers, or more commonly now it's just a block of RAM. And we can think of the stack as a pile of index cards. The first thing we do when we want to use the stack, boy, I cleaned up my gutters this weekend and I really beat up my hand. Sorry about that. But the first thing we need to do when we want to use the stack is we have to define what we call the base of the stack. So this is the address that we're going to put the stack. And so in this case we're doing a load extended immediate to the stack pointer 3FFF hex. And so that's going to put the base of the stack at 3FFF. So two terms that we need to remember. One is the base of the stack and the other is the top of the stack. Okay, so we're going to pretend that this is our stack. This is going to be the top of the stack, and this one back here is on the base of the stack. So let's say that's our stack. Okay, so right now we have an empty stack. The name aptly describes the function of a stack because we can only interact with the top of the stack. So we're not interacting by address, we're only interacting with the top of the stack. For example, one of the instructions that we can do to the stack is to push something onto the stack. So let's say that we're going to push a pair of registers, the BC registers, so that instruction is called push B onto the stack. Well, when we do that, the first thing that's going to happen is the processor is going to copy the value of the B register onto the stack, and then it's going to copy the value of the C register onto the stack. So now we've got 2 bytes on our stack. And the stack has now grown so that the top of the stack is now 2 bytes away from where the base was. So now we have a choice. We can either do another push, or we can take these things off the stack. And when we take things off the stack, that's called popping off the stack. So pushing puts things on the stack, popping takes things off the stack. So let's say we push the DE register pair. So first it's going to put down the D register, and then it's going to put down the E register. So now we've got 4 things on our stack. So again, we have a choice. We can either interact with the top of the stack, or we can put more things on the stack. So let's push the HL. So there's our H, there's our L. So now we've got all these things on the stack. Now we're going to pop something off the stack. So let's pop HL back. So this is going to go into the L register, and this is going to go into the H register. So we've popped those things off the stack. They're gone. This is the new top of the stack, so we're going to interact with that card. So you get the idea that it's all about the order. So let's take these back off. Let's reset our stack to that, and let's say that we've got some registers here. So here's our DE HL register pair, and this is what we've got in our registers. So these are our DE HL registers. Okay. So let's do that same example again. First thing we're going to do is push HL onto the stack. So when we push HL onto the stack, it's going to put H onto the stack, and it's going to put L onto the stack. Now push the HL. Now they're still over here in HL. We just made a copy of them. So there's our HL on the stack. Now we're going to push D onto the stack, which will push the DE pair onto the stack. So that's going to put D onto the stack, and that's going to put E onto the stack. Okay, great. We got 4 things in our stack. Now we're going to pop these. So first we did a push H, and then we did a push D. Now let's do a pop H and a pop D. So let's pop H. So this is going to go there, and this is going to go there. And now we pop DE pair. So this is going to go there. This is going to go there. And so you look at what's happened is we have simply reversed the DE pair and the HL pair. We've exchanged those. So that's the same as if we had done the exchange instruction, the XCHG instruction. We swapped the DE pair with the HL pair. So it's all about the order. When we're doing instructions on the stack, we don't do a push and a pop in the same order. We have to do it in the inverse order, or else we wind up exchanging things. And sometimes we want to exchange things, but sometimes we don't. Now, using the stack is a terribly inefficient way of exchanging things. It took us 4 instructions, where the DEHL exchange is a single instruction, and it's not particularly quick. Each push or pop on the stack took 10 or 12 T-states, where the exchange only takes something like 7 T-states. So the exchange is a much quicker instruction, and it's a much smaller instruction. But there isn't an exchange between all the register pairs. Sometimes we just need to do things with other register pairs other than what the exchange instruction can handle. But at any rate, the stack push and pop is not always the fastest, but quite often it's the most convenient because we can do a lot with a single byte instruction. Okay, here's an example that's more of a real-world example. Let's say that we've got a subroutine, and the first thing we want to do in this subroutine is save the accumulator, because we're going to use the accumulator for other things. So we come to our subroutine, and the first thing we're going to do is a push PSW. That's our program status word. That's the accumulator and all the flags. So we push the PSW. That saves it to the stack. We then do some other things. We're going to move something in A. We're going to output that. We're going to input that. We're going to move that to the memory location. And then we're going to pop the PSW. So we're going to restore the accumulator and the flags to what it was before. And so we do a pop PSW. So this is typically how we're going to use the push and pop, just to temporarily save something, to save a register pair, and then when we're done with whatever we're doing, we're going to restore it back to where it was before. Okay, behind the scenes, there's a register called the stack pointer. So that's a word register, it's a 2-byte register, and it is pointing to the top of the stack. So when we had all of these things on our stack, right now the stack pointer is at 3FFF hex. We have 4 things on the stack, and so the stack pointer is now 4 bytes away from that. Okay, key point. The base is the first location of the stack. The top of the stack is going to be at a memory location that is lower than the base. In other words, the stack grows downward. Every time we put something on the stack, the number is getting smaller for the stack pointer. So again, for example, stack pointer now is 3FFF. We put something on the stack, we're now at 3FFE, 3FFD, 3FFC, 3FFB. So we are growing the stack downwards. So the base of the stack is the highest memory location. The top of the stack is going to be the lower memory location. So the top of the stack is always less than the base. Okay, important thing to remember, the stack is growing downwards. We have instructions we can set and reset and manipulate the stack pointer, and this gives us a lot of flexibility. But typically when we're doing something just like with a push and a pop, the stack pointer takes care of itself. So anytime that we do a pop, it increments the stack pointer, because remember, a pop is taking things off the stack, and so we're getting closer to the base, so it increments the stack pointer. Anytime we do a push, it decrements the stack pointer, because again, we do a push, we're putting something onto the stack is moving downwards, and so the stack pointer is getting to a smaller value. When we read the stack or pop something off the stack, we're not actually destroying that memory location. So whatever we left in there is still there. So if we're doing some fancy stack manipulation or some fancy memory manipulation, the stuff is still there. We're not actually destroying it. But when we do pop something off the stack, so let's say we have these on the stack and we're going to do a pop D, whatever was in D is now gone. The DE pair gets destroyed when we do a pop. When we do a push, we're just duplicating these onto the stack. We're not actually destroying them. So the flexibility of the stack leaves it wide open for abuse, and we'll talk a little bit about that later. But the stack is very powerful, but it's also very dangerous. Now there's 14 instructions that can be used with the stack. And interestingly enough, if you have your copy of the either the 8080 assembly manual or your 8080 user's manual or the 8085 user's manual, it's interesting that all these manuals only talk about 13 instructions, but there's actually 14 instructions that manipulate the stack. So let's look at those. Okay, so we already talked about we have the push and the pop for the 4 register pairs, including the accumulator and the program status word. So we have push B, push D, push H, and push PSW. Now each of those push instructions move the stack pointer 2 bytes away from the base, so 2 bytes lower than the base. We have the equivalent pops, pop B, D, H, and PSW, and those move the stack pointer 2 bytes towards the base. We have the exchange, the XTHL instruction, that exchange the 2 bytes on the top of the stack with the H and the L. So, for example, if we have these on the stack and these on H and L, when we do the XTHL, we're actually just swapping. We're not changing the location of the stack pointer. So effectively what this is going to do is it's going to take this value and put that into H, this value, put that into L, put that value into H, and then it's going to be like that. So basically we've swapped the data. So the XTHL is swapping the data. The SPHL is different. It's replacing the address of the stack, so that 3FFF, it's replacing that with whatever's in the HL pair. So if we do SPHL, that's going to change this 3FFFH to 5132. Okay, so that would change it from that address to this address. So with the XTHL, we're working with the data. With the SPHL, we're actually changing the pointer. We can LXI, load extended immediate, the stack pointer, and so that's what we did to begin with, to tell it where we wanted the stack pointer. Then we can increment or decrement the stack pointer. And remember, increment and decrement only move the stack pointer by 1 byte. So where a push or a pop moved it by 2, increment and decrement only move it by 1. So that can get us in trouble if we don't think that through completely. And finally, the instruction that's not listed is one of the instructions I use the most, and that's the double register add with the stack pointer. So what this does is it will add whatever the value of the stack pointer, in this case with an empty stack, it would be the base, the 3FFF hex, it'll add that to the HL pair. The reason the DAD is a handy instruction is because that's a way to get the stack pointer if we want to use it for something else. So we can clear the HL pair, and then we can do a DAD with the stack pointer, and that will then put whatever the stack pointer is into the HL pair without exchanging them, copying them, and having. So this all sounds simple. Why is there phobia for the stack pointer, and how does that wind up getting people into trouble? And the reason people can get into trouble is that when you're programming, you're unconsciously using the stack, because any time that you do a call instruction, the program is putting an address into the stack. For example, let's say our program has a call. So I call a sub, and let's say that this is at address 1231. As soon as I get to this instruction, the next instruction down is going to be 1, 2, 3, 4, because this is 1, 2, 3 bytes long. So our next instruction, and let's say this is just just do something else. So when the program gets here, and when it's on this instruction, the program counter is going to have the number, the address 1, 2, 3, 4. Okay, so here's my program counter 1, 2, 3, 4. As soon as it executes this call instruction, it takes the program counter and puts that onto the stack. So our stack then is going to have 1, 2, 3, 4 on our stack, because that's the next instruction that's going to be executed. That's what our program counter has. Now our program counter is changed to whatever this subroutine address is at. So we go off, we do that subroutine, and when we're on that subroutine, we can do whatever we want to the stack. We can push things onto the stack, we can increment the stack, decrement the stack, pop things, move the stack, we can do whatever we want to the stack. We just have to remember that at the end of that subroutine, we're going to have a return instruction. That return instruction is going to take this value that was on the stack and put it back into the program counter. So the program counter, this 3, 4, is going to go into the low byte. 1, 2 is going to go into the high byte. It's going to restore our program counter to the 1, 2, 3, 4, and that's where our program is going to continue execution. The upshot is that when we go off and address and do a subroutine, we can push things onto the stack to save them. We can then pop things after to restore them, but we have to make sure we left the stack exactly the way it was, because this program counter on the return is going to get restored to the value that was left on the stack. And if we've messed with the stack, we mess with that program counter. So what are the problems? Well, the pops have to be in the reverse order of the pushes, or the data gets mixed around. We already talked about that. Returns have to be used with calls, or you explicitly have to pop a value off the stack. So if you go and call a routine, you have to return from that routine. You can't you can't jump back from that routine. When you push something on the stack, you have to pop something off the stack. So if you have a little loop where you're pushing and popping, you have to make sure that every time you're going through that loop, those even out. Because what would happen if you continually push things onto the stack more than you pop things off, your stack is going to continue to grow. You have to remember that push and pop move the stack by 2 bytes, where increment and decrement only move the stack by 1 byte. Okay, here's some snippets of code that can cause stack problems. Here's a push H, push program status word, pop H, pop PSW. This is what we just talked about to begin with, is that while a beginner might think that the order of the pushes and pops have to be in the same order, they actually have to be in the reverse order, because the last thing you put on is the first thing that comes off. Another example is where you call a subroutine and then you jump back. So you call the subroutine, you jump back, and this left the program counter on the stack. So now your stack is down by 2 additional bytes. Every time you were to do this, you would wind up leaving 2 bytes on the stack. Third example is where you push something onto the stack and then you call a subroutine, and the intent is that you want to then retrieve that value you pushed onto the stack. Remember, this call instruction has pushed the program counter onto the stack, so now there's the program counter and then there's your BC register pair. You go to your subroutine and you say, without thinking, you say, okay, well now I'm going to pop the BC register back, and then I'm going to do some stuff. When you thought you popped the BC register pair, you were actually popping the return program counter. And now when you do the return, you're actually loading the program counter with whatever was in the BC register pair. Maybe that's what you wanted, but maybe not. If you do this, the program's going to start from whatever value was in the BC pair. It's probably not what you intended. So where is the stack? Well, on the 4004 and the 8008, the stack was internal to the processor. The 4004 had 3 registers that were the stack, and the 8008 had 8 registers that were the stack. It's pretty convenient back then because you didn't have to do any initialization of the stack. It was all taken care of for you. It was what we call now a circular buffer, really, these registers. The 8080 stack is the first one to become external to the CPU. So it was no longer registers, it was in external memory. And that external memory could be dedicated memory that was hardwired, and there's select pins that could be used to select that memory space, or it could have just been part of the system RAM. In the 8080, it could have been either way. It could have been shared, or it could have been dedicated hardware. In the 8085 and after, that flexibility went away, and so now the stack was just built in to be in the shared memory space. There wasn't the hardware mechanism that would allow you to do a chip select on dedicated RAM for the stack. So the upshot is, in the 8080 and after, because it's not internal to the processor and taken care of for us, we have to locate the stack. So we have to specify the base of the stack, which is, again, the highest address for the stack. In other words, the stack is upside down. The stack grows downwards from there. So if we set the stack pointer to 4FFF, we push B, that puts 2 bytes onto the stack, and move the stack pointer down by 2 locations. Okay, in general, the general practice is to place the stack at the top of the RAM above the program space. Now, if we have a single board computer, it's probably fairly common to put the stack in the RAM that's local to that single board computer, and if we have additional RAM off board, then we would use that just for program space. So I think it's more common to put the stack in your local RAM if you have it, if you're on a single board computer. Key thing, remember the stack is growing towards your data and your program. So if more items are put onto the stack than removed, these items will eventually begin to overwrite the stack or whatever data you have down into RAM, and that's called a runaway stack. So now you're changing your program by whatever values you're pushing onto the stack. Probably not intentionally. The stack can be used in all sorts of tricky manners. To some degree, these tricks are convenient and they're commonly used. For example, things like a jump table or branch tables are a simple way to you manipulate the stack by pushing a value onto the stack kind of artificially, and then you do a jump to a subroutine, and then from that subroutine you do a return, and that'll take you back to the value that you artificially pushed onto the stack. So that's commonly done, but there's a limit between the program having panache and doing these slick little things and just being a pain in the arse when you can't remember what you were doing later. You were so tricky at the time. Okay, well, that's all I wanted to say about the stack. That should be enough information to get going and use the stack. So just remember to be careful with the stack, and if your program starts to act erratically, there's a good chance that maybe you just have a runaway stack. Okay, well, next time we'll talk about the history of the stack and for the 4004 and the 8008. But that's it. Thanks for watching. Bye.